Hello and welcome back to a new video here on the Fusel channel in my D3D12Ez video series. Now in today's video I wanna play a bit around with our code, show you what you can do more with it, how you can improve the code a bit, and yeah, just play a bit around, talk a bit about more concepts that we have in DirectX 12 and in HLSL, and then we will call it a day. And then we're gonna be finished with EZ. So basically EZ is finished after this video. We made it to a colored triangle on the screen. Everything else will then be done in a new video series. This will all translate into like real-time rendering, as I at some point pointed out. Maybe I've already pointed it out, maybe not. But basically D3D12Ez, the codebase will be rewritten into a framework for real-time rendering. And while I am rewriting that into videos on the rewriting, I might also do a primer on a bit of math topics that you need to know. And maybe I'm also gonna do a video series about concepts of real-time rendering. However, this is like a big topic and it's hard to kind of like differentiate on what we want to do, and maybe I want to stay more on the ad hoc approach and do it a bit more straightforward with code so that we do not have too much of theory before we're gonna get coding. Same with like the math series. The math series will not be required for watching the further videos, but will be recommended. So we are back in our code base and I want to do a few things and play a bit around. Now if you scroll down here, you can see that we are currently drawing a triangle here with the scissor rectangles, and then we're gonna somewhere down here draw it after we set up the root signature. And what you can also see that we had this puke color in here, and if we started with a 5, you're gonna see that puke color is no longer a thing, right? It's not a thing, it's just a colored triangle, but there's no color puking. And that's the first thing that I want to fix, because the color puking was nice, so maybe let's add color puking in here. Now there are multiple ways on how we can do color puking now. Now first of all, it will all happen in the pixel shader, because there we have the color for puking. I'm gonna maybe rename this to puke because it's making a bit more sense now. And we have our texel that we have requested or sampled from the texture. Now there are multiple ways of doing both things. Now first of all, the texel is loaded, that's completely correct, and then it's composed to a new color value. And now what I want to do basically is I want to now add a contribution of my color puking. So what you could do is, for example, just add these two values together, RGB plus color puking, and you can see that actually we get a color puking now again, because basically we are adding this to the color values of the texel. However, as you can see, it's all a bit overexposed. And with overexposed, I mean that it's kind of like very, very bright white every time I kind of like one color channel overshoot. So bright white, bright yellow, it's kind of like very bright, right? This is a problem. This is because the way of color puking works, because color puking is between 0 and 1. The texels are between 0 and 1, and we are adding them together, so we are actually going over 1. In the worst case, we are actually at a color value of 2, which is of course not correct, and it will be clamped to 1. Another way of doing it would be to actually multiply it, because puking is basically a factor between 0 and 1, and our texel is a value between 0 and 1. We take our texel and multiply it by the puke color, which basically means that we attenuate it by the value of puking. And now you can see that we actually have a color puking triangle that's not overexposed. You can see that it goes from black, first the red channel goes up, then the yellow channel goes up, the green channel goes up, but it looks yellow. And then the blue channel goes up until we are getting the normally colored triangle. So this is a bit more nicer color puking on this triangle, and this is basically where I want to stay. Now one thing that we have a problem currently is that our triangle is currently in the center of our screen. I want to fix that. I don't want to only have it in the center of our screen. I actually want to move this triangle a bit around and have a bit more control where it is. Now how do we do that? Now first of all, I want to apply something called aspect ratio correction. Currently, if I press F11 and go out of the full screen mode, you can see no matter how I resize my window, the triangle will always fit in inside of the bounds of the window. So as you can see, if I make it that big, it will always be at the bottom left, at the top center, and at the bottom right. It's always going to be that way. There's no way around that. Of course, here it's a bit cropped because of how Windows works, but if I make it full screen, it kind of like works again. And this is basically a fact. The triangle will always be the aspect ratio of the window. And that's what I want to correct today. I want to correct that by applying a so-called aspect ratio correction. So basically what I want to do is I want to yeah, kind of like make sure that on the left and on the right we have kind of like a border of just the background color and not only the triangle. Now, how do we do that? First of all, we need the aspect ratio. How do we get the aspect ratio of our window? Well, we should have a get width and a get height function, I think. If we have the get width and get height functions, we can find out how we're going to do it. Well, in general, if we have 500 divided by 500, so width divided by height, and both are the same, the factor is 1, which is exactly okay, because now the width and the height is the same, and we don't need any corrections. Now, if we have a width of 1000, and we have a height of 500, you can see that we have a factor of 2. Now this factor of 2 is actually not the correct factor that we want, because this would be the scaling factor in the height. Now if we kind of like want to make sure we kind of like scale in the height, then this would be correct, because now the height would need to be multiplied by 2. But what we want to do is we want to get a scaling factor for the width, and to get a scaling factor from the width, we take the height divided by the width. In this case it's 0.5, and we know that we need to make it 0.5 smaller, the triangle. Now this needs to be done programmatically on the CPU side. I'm going to write a struct for that actually. Yeah, maybe do I want to, yeah. Let's write a struct for that so that we can do that. Vertex data, we can write that just in the main, right? Before we, same way we did our color puking. Here in the update, I can write a struct, let's call this one struct, arguments, or let's call it correction. So we're going to create a struct called correction, and the struct correction is going to have a aspect ratio in here, and then I'm going to create an instance of that correction, and correction, let's maybe capitalize this, and we have correction, we can do it like that, and then we have the aspect ratio, and the aspect ratio is going to be equal to the let's maybe do it like that, so that we have a bit of better formatting going on here. The GFX window, how did I call the window? DX window get, DX window get. And then we can get the height and divide it by the width. Of course, it needs to be done like that. And then it, of course, also needs to be converted to a float, so that we do the proper math calculations. Because if we don't convert it to float, it's going to be cropped off. And then we're going to get the width. I'm also going to convert that one to a float. And then there we go, we have the member set it up. Now we have the correct correction. Now the only thing that we need to do is we need to actually apply the correction on the GPU side. I don't want to apply it on the CPU side. We could apply it on the CPU side, but I want to do it on the GPU side, because this is something you commonly do on the GPU side, because you don't want to resize all of your geometry and rescale all your geometry as soon as your window changes its size. So it should be done on the GPU, and to be more specific, it should be actually done on the vertex shader. So to do that on the vertex shader, I'm actually going to replicate the struct, and I like to have its own header for all of the structs. So I'm gonna have I'm gonna call it pipe line.h.li, because it's kind of like a header for our whole pipeline. And then I'm gonna, the method of operation is not implemented. That's amazing. It's still going to create it. I had this problem multiple times, but the header is still going to be created here. All right, so what I'm going to do is I'm going to define a struct. I'm going to call that one correction, because this is going to be the struct for all of our correction data. And inside of here, we're going to have a float aspect ratio. Now we have replicated the struct on the GPU side. This works like that. And now we just need to use it. And to use it, we first need some memory on it. So I'm going to go into my root signature. We could also define kind of like the root signature in the pipeline. This would be also possible, but I'm going to do it like that currently. Now what I want to do is I want to duplicate that line, and I want to have another set of root constants. This time they're going to start at buffer 1, and we're just going to have 1 in here, which basically means that we shifted everything by 1. So the descriptor table is now at 2, and now we have a float 1. Actually, this is not a float 1, this is a correction struct, and this is basically my correction data, because we now basically have a struct. And what we need to do now to use that struct is we need to kind of like map a instance of the struct to the register B1. How can we do that? Well, in the pixel shader, we basically had the float puke at the register B0. And if we want to bind a struct to that, in this case, we're going to do it in the vertex shader because the vertex shader is there for processing geometry data. I'm not going to bind the float 1. I'm actually going to include another header here. And I am going to include my pipe line.hlsli, which stands for HLSL include. The root signature should also be an HLSLI file. However, since it still gets compiled, I tend to most of the time call it HLSL. Now, instead of the data type puke, I'm going to call the data type correction, and the instance is going to be correction in lower caps, and then I'm going to bind that to the register B1. And what I now can do is I can take my correction and I can apply that. How do I apply that? Well, basically what we need to do, we need to apply it to the X value. So what I'm going to do is I'm basically going to extract it. I'm going to have a float to px, and I'm going to basically set px equal to pos, and then I can do px x value, because that's what I want to scale, times equal correction aspect ratio. Then the correction is applied, and instead of directly using the position, yeah, we can do this like that fully, I can basically implement px here. And now you can see the correction should be applied to the x coordinate. Now, how do I now fill the data? Well, of course, in the main, first of all, the heap has gone to 2. And now we again need to set graphics root constants. This time, since slot 1, we have one thing that we want to set. And now we want to actually set the correction struct. So this is basically the idea. Now we are setting the correction struct, just one float with an offset of 0 to slot 1. And now I would suspect that we get a bit of aspect ratio correction in there, if I done everything correctly. And we do get nothing. Why do we get nothing? Well, because something has obviously gone wrong. Now, what has gone wrong? Actually, this is something very interesting that can happen in these cases. Now, we can take a look if we get an error message here. We probably do not get an error message here. And this is now the time where you are questioning your whole, like, the HLSL DirectX 12 knowledge. However, I want to try to show you what's happening by opening Nsight Graphics. Let's quickly open Nsight Graphics. I hope Nsight Graphics was the tool where I could see that. I had a similar issue quite a while ago. Am I on release? Yeah, I'm on release. Yeah, if I'm on release, I wouldn't even have gotten a message in here, but that's not a problem here because the debug layer would probably not have helped us. But I want to show you what's going on. That is the frame. You can capture it. And you can see that we're still going to have all of our events, but you can see that actually our triangle looks like that. You can see our triangle is still drawn, but basically its value is 0. The triangle's value is or not the value is 0, but kind of like the all x values are 0, which means that we have a solid line with an area of 0, and so it's not drawn. And this is probably going to happen because the value of our constant was 0. You can see it tried to set it. It's in here in the pipeline, but as it seems, it is kind of like 0. How can we inspect it a bit better? We can go to the draw instance section, and what you can do is you can take a look at the several stages, and you can also take a look at the 32-bit constants that has been passed. For example, for the vertex shader, buffer 0 has been bound and 3 values have been bound. However, you can see that we kind of like do not see our other values that we had. You can see 0 to 0 had been bound, but everything else was not bound. You can see here, you can take a look at the root parameters, and you can actually take a look at the values, but you can see that no constant buffer used by the shader. So something has obviously not gone right. You can see this has been somehow set. to an aspect ratio, but it was at index 0 with 3 values, and something obviously has gone wrong. Something is not correct. This is like my setup. You can see that the descriptors are working still for our texture. You can see that there is a bit of a problem here because it kind of like tries to map the correction to the index 0, and the value is also 0, so something has gone wrong. What has gone wrong? I don't know. Let's inspect it. From what I am seeing in Inside Graphics, it was kind of like suggesting that value is wrong, but however it is not. Now there are multiple ways of trying to fix that. The most important way that I would always recommend dealing with these kind of problems is to have everything aligned, by basically putting all of these values to 4. This is one thing that you can try out. And as you can see, if I apply these, it magically comes back. And this is really important when working with these constants. Do never use values other than 4 if you have some constants following in a row. Because basically what the GPU is going to do, or what the shader is going to do, it's going to pack these. Actually, if these are like 3 and 1, I think it's trying to pack them. However, what I would recommend is just always, if you're using one of these slots, always use 4. As you can see, it is a bit of a madness. It is as it is. I would not recommend you doing that. And as you can see, the debugger is not even giving you correct informations. The root parameters here are not aligned correctly. You cannot see how they work. This is a bit of an odd bug, and this is a bug that I tried to search or invested ages into that, and when I first occurred that bug in my code, so I went into Inside Graphics, and the whole layout in Inside Graphics was not matching the layout that I have implemented in my root signature. So I played it around for several like hours, and then I found out if I align it to 4, it always kind of work. It's as it is. Just do it, and probably it's the best way of just aligning it always. And now you can see we get a correctly aspect ratio corrected image. We could go in and measure the pixels. However, as you can see, these are correct. And if I start resizing my window, you can see that the actual size of the triangle changes. So you can see that it kind of like gets stretched. And as soon as I let go and the swap chain resizes, you can see that we have now a correctly fitted in triangle. If I change my width here, you can see it also works. If I go into extremes, you can see that it kind of works, but it's no longer kind of like fitting. Now in this case, you would actually want to do aspect ratio correction on the Y axis, not on the width, on the height, an aspect ratio correction, but this is kind of like a conditioner that you would need to check. So you would have actually a correction value for X, and you would have a correction value for Y, and you would kind of like check if the width is bigger than the height, and if the width is bigger than the height, then you do the correction to X, otherwise to Y, and you have multiple formulas for these corrections, and you always take the correct one. I don't want to go too much into the details, since we're always going to do like 60:9, so we're always going to have that aspect ratio, and you can see that this aspect ratio is working fine as it should. Alright, so now we have aspect ratio correction, and now what I want to do is I want to apply a bit more control over our triangle, and what I now want to do is I want to have a general zoom factor. So I want to have a factor to make the triangle bigger and smaller, so basically to zoom it. Now the first thing is I'm going to adapt my struct here, so I'm going to add a float zoom value to it. So this is kind of like a value, how much we want to zoom in and out. And I want to basically add a zoom value of 0.8 just to not have the triangle stick to the edges of the window. So a static value just to 0.8. Now, of course, this value needs to be reflected on the GPU as well. The root signature is already prepared. We can have 4 values on here. Everything is fine. And the only thing that I need to do is I need to go to my pipeline and add the zoom value in here as well. And since this is all already bound, the zoom value is automatically ready for the vertex shader, and now I can use the zoom value in the vertex shader. Now, when do I use the vertex shader? Now, there are certain rules on how you do a transformation of points, and the rules of transformation, is something called model view projection. This is the order that everything shall follow. First a so-called model transform, then a so-called view transform, and then a so-called projection transform. The model transform is a transform that is dependent on how we want to position our model. In this case, the model is the triangle. So if we want to zoom in or out our triangle, this is the first thing that we shall apply, because the first transformation is the model transformation. The next transformation that you would apply is the so-called view transformation. The view transformation is kind of like the camera view of the thing. So if you're writing a 2D game, first you kind of like transform your models into like 2D space and kind of like have them like scaled and things like that, and then you apply the view. The view is dependent on where the player is currently in your 2D level, for example, and you kind of like move it so that it's on the correct location on the screen, dependent on the camera. And the last thing that you do is you apply the projection, and the projection maps your 2D or 3-dimensional geometry onto the 2-dimensional window. And the 2-dimensional window that we currently have only has one projection transform that we are doing, and the currently transform that we are doing for projection is the aspect ratio correction. So this is basically our projection. This is the projection, that's the one that we want to have. Now what we want to apply is the so-called model transform, so we want to actually zoom it in and out, and this is basically done by multiplying the whole px value by the correction zoom. This is our view transform. No, not view, model, our model transform, because our model shall be zoomed or not zoomed. We could also see it kind of like as a view. We can also see it as a view. We can also see the zoom as the camera zoom to the screen. This is also possible. This kind of like depends on how you define it. These are just like certain rules, and on the order how you do them. First you do everything that's related to the model, then you transform the model to the space where you're currently looking at it, and then you're doing the projection into the window. And the view could be, for example, the zoom, and the model could be the zoom. We could have the zoom based on the models level, or we could have the zoom based on the views level. Since we're also going to do model transformation, maybe I'm just going to set the correction zoom as a view projection here. And now if I have the zoom in here, what I would suspect to see is basically a zoomed out triangle, and we do not get anything. Okay, why do I not get anything? Maybe because we have not correctly transformed this. Yes, as you can see, I just have transformed one constant. So let's add actually something called padding. Let's add something called pad. This is padding. If you are doing things like that, you should add padding sometimes, and then I can directly upload like 4 values, and then everything is correct, and now we should have the zoom value also uploaded to the GPU. And now you can see that our triangle is actually zoomed out. Of course, the zoom is now related to the window size. If I make the window smaller, the zoom kind of like gets smaller as well. And if I make it bigger, the zoom gets bigger, because it's not like normalized to the window size. However, as you can see, we are correctly zoomed in. And that's nice. So we have now a bit of transformation applied. We have our camera that kind of like zoomed out from the normalized device coordinates. Then we have a bit of projection applied to kind of like fix the aspect ratio correction. And now we have a triangle inside of the screen. And now I want to do one more thing. Now I want to rotate my triangle. And this is now actually going to be our model projection. Or not our projection, our model transformation. So the model shall be rotated, the view shall be zoomed out, and the projection shall be correct the aspect ratio. That's what I want to do. Now, how do I apply a rotation? Well, I want to do the rotation completely on the GPU. And therefore, I want to transform 2 components to the rotation. We're going to, in a second, find out how rotation works. Or maybe we should find out how rotation works first. Right. So how can we find out how rotation works? Well, we could go to ChatGPT and ask it. However, it's actually simple. 2D point rotation is a very simple thing. 2D rotations. Let's click on that one. And maybe we're going to find a code that's doing it, and this is actually the right way of doing it. So we can find out the x and then the new x value and the new y value of a point by applying these 2 equations to rotate a point around the origin. And that's exactly what we want to do. We want to rotate it around the origin. Now, as you can see, we have cosinus and sinus going on here. And as you can see, the cosinus and sinus are always taken of one angle, and that's exactly what we want to do. So cosinus and sinus are going to be the values that we're going to transform to the GPU actually. So actually what I'm going to do, instead of directly kind of like applying this angle at the GPU, I actually want to apply the angle, sinus and cosinus value. So instead of just having something like the angle in here, something like that, I actually want to have the sine angle, and I want to have the cosine angle. So I'm basically going to compute the angle values on the CPU side, and then I'm going to transform them on the GPU. Of course, the GPU could also do sinus and cosinus, however, that's not what I want to do currently. Now, the vertex shader is actually going to be quite easy. We're going to construct our float px, not directly from the original value. We're going to construct it from, yeah, we can also, let's maybe, no, we're gonna just have it empty, and then we're gonna set x to something, and we're gonna set y to something. And this is basically our model projection. Now, how does x work? X is x0 times the cosine component minus y, the sine component. We can try to copy this down and then adapt it. Let's see how this turns out. Oh, it's actually converted this quite easily. The only thing that it doesn't like are, of course, these characters. So what I want to do is I have the x0, the x is now coming from the position x, and we're gonna multiply this by the, I need to stop pressing the the save button as long as I have these characters in here. So this was the cosinus component, right? Was it cosine? Yeah, say it. This is the cosine component. So correction, the where is my angle? It's not doing it because of that character, right? Why do you not have problems here? It's currently not giving me the cosine, so let's copy it. And then I say minus y0 position y times correction. Now we have it, the sine. What is the problem? Do you need brackets around these? Why should you? It's somehow currently not accepting what I want to do. And this is also the y component. It's probably because I copied the text and now it's on a different format, right? Yep, that's the right. It's not a minus. That is some arbitrary sign that I have copied over. So this is kind of like the idea of the equation, of the model projection here. And this is the same that we need down here. The only difference is that we had plus here and that we had sine and cosine as far as I'm concerned. Sine and cosine, x and y, and plus between. And this is now basically applying the rotation in here. Now the only thing that we need to do is we need to compute the components on the GPU side. So instead of padding, we have the sine angle and the cosine angle. So how do we compute them? Well, it's actually quite easy. We're gonna set the sine to sine f. Yeah, there we go, sine f. I was a bit confused currently. The cosine angle to cosine f, and then we need an angle that we actually compute. So I'm gonna add a static float angle, and the angle is gonna start at 0. And what we're gonna do is every frame we're gonna increment it by a certain value. We're gonna put this value low for starters. Then we're going to put in the angle in here, and then we have the sine component, the cosine component of the angle that then going to flow through the pipeline correction into the vertex shader. And then we would suspect that we get a bit of a rotation of our triangle. And let's take a look at that. And now you can see that our triangle is actually rotating on the screen, as it should do, because we applied a rotation to it. It's still color puking and it's rotating quite slowly. Let's increase that a bit, the speed. Actually, the speed is currently, it's not kind of like dependent of the time, it's only dependent of the frame time. But we can like make it 10 times faster so that it rotates a bit faster. Now if we run that, there we go. Now we get a rotating triangle, and you can actually see that it's rotating more or less correctly. Now, why do I do my transformations the way I do them? Now, the important thing is that rotation always works on the model around the center. And if you're doing the rotation after the projection, then bad things are going to happen, right? If we're going to play a bit around, I'm going to show you how to not do it. If we would, for example, like swap the aspect ratio and the zoom, this is still going to work because this is actually multiplication and we don't use matrices yet. As soon as we use matrices, it's going to break. However, if we would first apply the zoom, now this is a bit harder because it's actually not as simple. I need to apply, let's maybe apply the aspect ratio correction to, I don't know, I'm not quite sure if I can actually modify, I should be able to modify it. Let's apply the aspect ratio here to the position directly before I am gonna do the transformation. And if I apply the aspect ratio correction first and then I do the rotation, you can see that bad things are gonna happen. Because now, after I apply the aspect ratio correction, the triangle is no longer centered. And if it's no longer centered, it basically means that it kind of like stretches, because we applied the projection, the aspect ratio correction first. And this is not how it works, and bad things are gonna happen. And this is, of course, not what we want, right? So this is kind of like why we do it in this order. Currently, I'm doing first the model, then the view, then the projection. Now, why is it not changing the size or the shape if I change these two? Well, basically, it doesn't change it because it's just multiplication. It's just multiplication, and multiplication is kind of like not relevant in which order we're gonna do it. So this is really important to understand. In general, you should always do model, view, projection. This is the order that's always gonna happen. We're gonna have more videos, especially with real-time rendering, that's going to go into the details, but that's the most important thing. Model, view, projection. First, you're going to transform your geometries, or your geometries, right? Then you transform the geometry into the view, where it shall be located on the screen, or in your virtual world, not on the screen. And then you do projection, which is going to transform it into the view space onto the monitor, basically. Now, projection and view is always hard to get, and again, just as I try to explain it, I will again match them up, because it's kind of like the same, right? Putting it on the correct position and on the screen, and then on the screen for the user, it kind of like seems to be the same. But the view is kind of like putting it in, still in your virtual dimension, like model and view is all still virtual. It's virtual on this normalized device coordinates from -1 to 1. It's still in this normalized space. Model and view is still going to transform it in this virtual space, and then the projectors are actually going to put it into real world coordinates. And this is kind of like how it works. And this is a very simple way of doing it. This is a very simple way on like normal two-dimensional geometry. If we are going 3D, it's going to be way more computational intense and way more complicated, because then we have like a 4-component float with like X, Y, Z, and W, and basically we would just work with the OPOS, with this float 4. This is currently all transformation in 2-dimensional space, and down here we're just transforming it into a virtual 3-dimensional point that is basically just in a 2-dimensional plane. As you can see, many things that go on here. This one is something that we should also fix, but I think for the tutorial I'm going to keep it. But this is our video for today. We have adapted this a bit to make things nicer. Thank you for watching. See you in the next video. This was D3D12Ez, and the next following videos will be rewriting D3D12Ez into a new framework. Thank you for watching. Make sure to like and subscribe, and have a nice day. Bye.